Thank you. So I'm just, sorry, I'm just pulling up my presentation here. Um, so there we go. I'm hoping everyone can see the slides.
Yep, all good.
Perfect. So thank you so much for having me here today. My name's Pamela Brittain, and I'm the K-12 Academic Coordinator for the Fields Institute. I'm also a certified teacher in Ontario. I have a Master's of Mathematics, specifically for teachers, and a PhD in math education. My focus there was actually on elementary teacher candidates who struggle with basic arithmetic and numeracy. My research had showed that the majority of these teacher candidates were unable to solve basic arithmetic questions and were often so caught up on memorizing tricks and algorithms without understanding the why behind what they were doing that this developed a lot of math anxiety and fear of mathematics. And as a significant amount of research has actually shown, this anxiety can actually be passed on to their students when they become teachers. And this is especially true of female teachers to female students who are already underrepresented in higher mathematics education. So I've become very focused in my current work and passion, actually, on understanding the why and giving learners of mathematics a strong foundational knowledge of why the math they do works the way it does, and hopefully not only alleviating much of their math anxiety, but also helping them to appreciate math in a very different way. So, the question that we've probably all heard from our students, no matter what level we teach, is why should I learn this when my calculator, phone, computer, AI can do it for me? And even 25 years ago, I asked my high school math teacher why I needed to learn to do arithmetic calculations by hand. Why did I need to memorize my timetables? Why did I need to do things like mad minutes? They still make me cringe. When I have this handy little device, a calculator at the time, that can do it for me. The answer I was given was, well, you might not always have your calculator handy. Fast forward 25 years, and this is definitely no longer the case. I now have basically a little supercomputer in my pocket that goes absolutely everywhere I go. I don't leave the house without it. And younger generations, the ones many of us are currently teaching, are even more ingrained in this technology always available lifestyle. So now when they ask this very legitimate question, they often get many very unsatisfying answers, or they have teachers who really don't know how to answer the question. As an anecdote, my niece, who's now in grade 9, recently asked why she needs to learn the equation for slope, the y equals mx plus b. What was its relevance? Her teacher wasn't able to answer this, but her uncle, who works in data analysis, explained to her that this one equation is the basis of almost all modern AI and computing and data analysis. And much of the world around us wouldn't be possible without it. But this context, this history, wasn't taught to her. Only the equation and how to solve questions using it were part of her learning. And so, with this presentation, I hope to explore ways we can address this and provide some context and history on how we can answer this very valid question. So, we'll start off with a brief trip through history. This is what's called an Ashango bone. It's almost 20,000 years old, and it's considered the oldest mathematical tool of humankind. And most of math, or mathematics or numeracy, started off with tokens and counting tools like the Ashango bone to keep track of how much or how many of something that we had. Take sheep, for example. Let's say a farmer had sheep they were caring for. Historically, they would use a token or a stick to represent, or notches on a stick to represent each sheep. Each day, they would come out and compare the sheep to the tokens or the notches. If they had more sheep than notches, they'd gain some new sheep. Maybe somebody had a baby. If they had more notches than sheep, they'd lost some. Maybe one ran away during the night. It was a simplistic method to keep track of and count how much of something we had. They could also use these sticks or tokens to do simple addition or subtraction. So we start off with a stick with a certain number of lines. If they inherited more sheep or their sheep had babies, they'd add lines to it. If they lost or gave away some, they'd remove lines or tokens or even physically break the stick in order to indicate addition and subtraction. In fact, clay tokens from thousands of years ago were used to count sheep specifically. One sheep was actually uh, shown by two tokens. They also used different tokens for different amounts of things. Some of them were done in increments of sixes and tens and higher sexagesimal numbers. Now, where this worked fine for small, easily countable amounts, it quickly became more complex for larger amounts. Enter the numbers. So we created numbers using symbols, and this included things like Roman numerals, and eventually the evolution of what we refer to as the Hindu-Arabic number system, which uses the familiar 0 to 9 digits and place value in base 10 to count things and represent numbers. And we did this in order to simplify how we wrote numbers and how we counted and kept track of things. We then created operations in order to work with these numbers and perform calculations on them, such as addition, subtraction, multiplication, and division. No longer did we have to physically break sticks to subtract sheep from our flock or carve new lines into already full sticks when a new one was born. We could instead use numbers to, again, simplify. We could use multiplication to calculate cobs of corn in a field by multiplying rows by columns by cobs per stalk, instead of trying to count them individually. Or we could use division to determine how we could divide our land into equal parcels for growing different crops. I just want to say, notice how I'm using a lot of agricultural references right now, sheep and corn and land, because this is actually where most of the start of mathematics and arithmetic and numeracy came from. It actually was sparked by agricultural revolutions. And then this evolved into the rise of commerce when we needed to sell these things. So we now needed ways to count parts of things and to calculate debt. So we created fractions, decimals, negative numbers, and we could perform operations on these new number types as well. And as these transactions became more complex, so too did the math involved with them. So we then started creating algorithms to simplify our calculations, making them quicker and more efficient to do. So things like this, which is an expanded method of multiplying two numbers with decimals together, became this, which, as you can see, is much shorter and much faster to do. But the issue with this is that in the second example, the shorter example, how do we figure out how many decimal places are going to be in our final answer? This comes down to actually memorizing a rule to count the number of decimals in the numbers we're multiplying together and moving the decimal over that number of places in our final answer. It works. It gives us the right answer. But unlike in the expanded form, where about a third of the way down at the very end, if you can read it, there's two numbers where it says 4 over 100 times 1 over 100. That gives us an answer of 4 over 10,000. Using fractions, we know if the number's over 10,000, that's automatically 4 decimal places when we convert it to a decimal. So our expanded form clearly shows us why we have 4 decimal places in our final answer. The second method is faster, but it requires memorizing various rules, including things like regrouping, and having lots of underlying knowledge in order to be able to apply it to solve the questions. And it might not be obvious why we follow certain steps and what we're actually doing. The first method is much longer, and there's a lot more places for making errors. I know I made so many mistakes trying to figure out the fractional portions when I did this by hand, but it makes it very clear what's going on and why we're doing things, and how we end up with 4 decimal places and how the regrouping works, that isn't clear when we've simplified it down into our algorithm. So, what does technology have to do with this? You might be asking what this trip through history has to do with the focus of this conference, which is modern technology. And the answer is this. Modern technology, such as calculators, computers, and even AI, have given us tools to be even more efficient in our methods of calculating things, of performing operations on numbers. It's given us tools that can do our previously handwritten calculations in the blink of an eye. We don't have to memorize any rules or tips or tricks. We don't have to keep in mind what number goes where, when we have to line up the decimals and place value, and when we don't, how to do long division. Instead, all we have to do is punch in the correct sequence of numbers or equations and let the technology do its magic. As I said at the start, it begs the question, why do I need to learn this when technology can just do it for me? First of all, we need to ask, is this a bad thing? I personally don't think it is. I think computers and technology are just the natural extension of what we as humans have been doing for millennia, simplifying the arithmetic parts of mathematics to make it easier and faster on ourselves to do calculations and to move on to the bigger questions in math, what I like to call the fun parts of math, the parts that can really inspire and engage. And if we only have so many hours with our students, technology can allow us to focus on different areas other than the rote parts. So, does this mean we shouldn't teach rote? Absolutely not. But I think it does mean that we need to teach rote mathematics in a different way, where we are using it to provide background and context to the math that these concepts underlie, and not so much about memorizing how to do them. And so this brings me back to the title of the talk, Understanding the Why. I personally believe technology is not going anywhere, and I think most people agree. And I think that we should be teaching our students how to use it properly and with the critical thinking skills required to understand the answers it provides, including if the answers provided are correct. We all know that AI not only lies, but it lies so convincingly to make you believe it's correct. If you try asking ChatGPT to multiply two three-digit numbers together, you can see the crazy answer you get back. Tell it it's wrong, it apologizes, so it actually humanizes it and apologizes and gives you another wrong answer. Then if you ask to see the algorithm it uses, you can be prepared to be even more thoroughly confused as to what it's doing. So I believe that mathematics is far more than arithmetic and numeracy, and using technology is no different than using long division to do calculations faster than an expanded method. It's the next logical step in doing math calculations more effectively and quicker. But this means it becomes increasingly important to teach students about what is going on behind the scenes, just like showing them why we have four decimal places when multiplying, or why invert and multiply in fractions work, or what's really going on when we try to divide by zero. So I figured I'd look at a fun little example here, and it involves dividing by zero. When we teach division, we teach the rule that division by zero is not allowed or is undefined. To someone who studies math or computer science, this explanation is often enough. Oh, it's undefined. The definition of dividing by zero is undefined. That makes sense to me. I accept it. But many students, and even those in industry and in academia, don't understand why it's undefined and what is happening when we're trying to divide by zero and why it causes issues, like a runaway battleship. On September 21st, 1997, a division by zero error on board the USS Yorktown remote database manager brought down all the machines on the network, causing the ship's propulsion system to fail. This is a true story. But why? So I want to just look at a really quick example of division by zero. If we think of division as repeated subtraction, much like we think of multiplication as repeated addition, and the inverse of multiplication is division, and the inverse of addition is subtraction, then we can investigate division as such. I'm going to use 10 divided by 2 as our example. You can see here I've done a series of 10 divided by 2 is 8, 8 divided by 2 is 6, and so on. And if I count how many times I was able to subtract 2 from 10, I get my answer of 5. So 10 divided by 2 is 5. But what happens if we apply the same algorithm to 10 divided by 0? Our first step would be 10 minus 0 is 10. Well, okay, now we do 10 minus 0 is 10. And 10 minus 0 is 10. And 10 minus 0 is 10. And I'm guessing you're seeing a pattern already here. We've created a loop. And if we're looking at counting, we're going to be counting to infinity. So if we add a counter each time we do subtraction, and then end when it equals 0 or a decimal number of a specific length, if there are remainders, then this is never going to stop. So it's kind of equivalent to doing in computer programming. Let x equal the dividend, let y equal the divisor, x minus y is number, add 1 to the counter. If the number equals 0 or a decimal of specific length, exit, else take your number minus y and keep going, and then print your counter. I also greatly apologize to any computer programmers because I know that this is not proper programming. I'm just using it to illustrate a point of what could be going on behind the scenes. So this is what happened in the USS Yorktown. The programmer didn't hard code an error into the system or an escape protocol for what to do when dividing by 0. And so the system got stuck in a loop that filled up the memory and eventually shut down the propulsion system. I believe actually that it was Windows NT that they were using that caused the issue. So iPhones, other phones, calculators in general are hard coded to return an error of undefined, not a number or another error code when we try and divide by 0. And we often just accept this without knowing why. But explaining to students why division by 0 is undefined, giving them an example, allows them to understand what the technology is in fact doing and what we have to take into account when we're using that technology. So this brings me to the conclusion of the talk. Technology is here to stay, and our students are going to use it and encounter it in every aspect of their lives, both academic and non-academic. So whether you're teaching elementary level students, high school students, first year calculus, or higher level mathematics and its applications, I actually encourage you to allow students to use the technology available to them to its fullest and to use it to be more efficient in their mathematical calculations, but also to teach them the history of where those calculations come from, why they work the way they do, and how to evaluate if what their technology is doing and the answer it is giving is in fact correct and makes sense. We can do things like use use proofs and logic to create more critical thinking skills and give them questions that have errors in them. Can you see what's wrong with this proof of 1 equals 2 or 2 equals 1 in this case? We can use terms like we can't do this yet when introducing new topics. In elementary school, students are very, very often taught that we must subtract the smaller number from the larger number. But that only holds valid until we introduce negative numbers. So by using that tiny little term, yet, it helps to build trust actually with our students that math is not designed to trick them or that mathematicians lie because we keep changing the rules. There's the idea of only geniuses can do math. And there are tons of examples on social media with questions like this one that are they're specifically designed to trick people. Um, and they're not a clear representation of what mathematics actually is like. And they perpetuate the myth that you have to be a genius in order to be a mathematician. Making it cross-curricular allows us to link math with art and science and technology and music and the world around us to provide context and connections to math applications and even social issues as well. And to borrow from Dan, his talk earlier, we need to manage cognitive load and decide where we want to allocate our time and effort in math class. We are working towards training both academics who should be curious about the why and also those who will be going out into industry and in a world where they will be expected to use these tools in their daily lives and in their chosen fields of employment. So, teaching a little bit of history and a background of what's going on behind the scenes could be an incredibly powerful tool for not only helping them succeed, but also helping them to question and evaluate the information being provided to them instead of just blindly memorizing tricks and rules or plugging numbers and information into a computer and expecting the answer that comes back out to be automatically correct. By teaching underlying foundations of what's going on behind the scenes and behind their screens, we are helping to set our students up for success and understanding in an increasingly technology and information driven world. And if there's one thing that true mathematics can teach, it's how to question everything and develop those ever increasingly needed critical thinking skills. So thank you very much for the opportunity to speak here. Here's some of my contact information, including a link to the programs that I'm currently developing with Fields, and also my own personal website as well. So I'd be happy to take questions. And yeah, thank you again.
Thank you very much, Pam, for your great talk.